Hello. Excuse me, sir. I think you are muted, sir. I can't hear you, sir.
Oh, strange. So why nobody has earlier? Anyway, strange. Bismillahirrahmanirrahim. Welcome to lecture number 10, digital signal processing course. In the last lecture, we were discussing a few properties of discrete time Fourier transform, and we started with linearity and time shifting property. We say that linearity is a property that supports both time scaling and additivity property. So in time scaling property, what you are doing, you are multiplying your signal with some scaling factor, for example, alpha here and alpha on the right side, and beta here and beta on the Fourier transform as well. So if you scale it by alpha, its Fourier transform will also be scaled by alpha. And if you scale the signal x2 of n in time domain, its Fourier transform x2 e to raised per j omega will also be scaled by beta. So this alpha and beta is basically the scaling factor, and it supports the scaling property. And this edit plus sign is basically supporting the additivity property, and x3 of n is basically alpha x1 of n plus beta x2 of n. So x3 e to raise per j omega is alpha x1 e to raise per j omega plus beta x2 e to raise per j omega. So what is the advantage of this property? Since we have to deal a large complex signal and system, so we can break the signal into different parts, and then we need to take the Fourier transform of individual parts. In the end, we can add the individual Fourier transform of all parts, and this will give us the final Fourier transform of a signal or a system. So that is the use of this linearity property. Then we jump towards the time shifting property, and time shifting property says that if you have x of n and this x of n and its Fourier transform x e to raise per j omega, if you delay it by a factor of n naught, n minus n naught, its Fourier transform will be a multiply with the complex exponential. And if we compare it complex exponential with polar representation, so the value of power here is 1 because nothing is written over here, so its value is 1. And its phase is theta, other than j is basically the theta. So if we separate j, we left with minus omega n naught. So we'll have this minus omega naught. So if we plot r equal to 1, it's mean that its magnitude is 1 for all frequencies. So it's not changing the magnitude response of your system. So if we have some magnitude response here, so it is multiplied by 1, we will get the same magnitude response. And if we plot the phase response, we will get this. Let me change the color, take the red color. So this will be the minus omega n naught. This is minus omega n naught. This minus sign indicate that this is decreasing function. So this is 0, this is omega axis, so it has linear uh, phase response. So from previous discussion, we said that if the phase response is linear, then we are okay. We don't need to worry about it. So it's linear phase response. So we are quite happy about it, right? So in conclusion, we can say that the time shifting property will not harm the magnitude or the phase response of our signal or a system. So that's why we are quite happy and with the delay property, because in reality it's always a delay between transmitter and receiver. For example, if I am talking to you, so it seems that there is no delay and you are listening to me with a zero delay time period. However, there is some delay in terms of millisecond, and but uh, Allah subhanahu wa ta'ala basically made our ears in such a way that it can ignore certain type of errors. So you can't basically understand that there is some delay. Like, so millisecond delay would not be recognizable by your ears. So you are feeling that I'm talking to you uh, in a real time basis, but there is some delay in milliseconds. So whenever there is a transmitter and reception pair, or whenever there is a communication between one party and another party, there is some delay. If we talk about the 4G system, so we are getting delay between transmitter and receiver whenever you make a call, you will get up to 30 milliseconds. But honestly, you never feel such delay in your life, right? So it's clear now.
Yes, sir.
Yes, sir.
Okay. Okay. The third property is the frequency shifting property. This is uh, similar to second property, but slightly different, and it's the backbone of your communication. Let me write it. Third one is the frequency shifting. Frequency shifting property. Frequency shifting property saying that uh, if you have Fourier transform x of n x e to raise per j omega, uh, despite of the delay, if we multiply your x of n with complex exponential e to raise per minus j omega not, let me put it in subscript, minus j omega not n, and let me take the entire in superscript, this one. So if we, let me put dot operation here, it's better if we put multiply sign here. If we multiply this with complex exponential, then the response would be x of omega minus omega naught, minus omega naught. Let me bring it in subscript so it will be recognizable for you. Let me close the bracket. So this is the frequency shifting property. If you have x of naught, let me make it little bit bigger so that you may get clear visibility. X of n, x e to raise per j omega. And if we multiply it with the complex exponential e to raise per minus j omega n, it would be shift from zero baseband signal to band pass signal, right? So what we are doing, we are changing the frequency spectra of the signal. So if your signal is a band pass signal around zero, it will be shifted to some frequency omega naught. This property, there are different name of this property. For example, we can call it a modulation property as well. We call it mixing property as well. We call it heterodyning property as well, right? So same property but different name. uh, Mixing, modulation, uh, heterodyning, and there is one term more, I guess, uh, frequency shifting, modulation, mixing. There is one more name, let me remember it. Have you studied about super heterodyning receiver during your communication system course? So there you are bringing your signal back to lower frequency, omega 1 to omega 2, intentionally. Anyway, this is the crisps of this property, frequency shifting property, modulation property, and mixing property. So let me explain with an example. So let me take green color here, and let me draw a line here, because we are going to time and frequency domain. So let's assume this is your time domain and this is your frequency domain. Right, so this is time and this is your frequency. So let's assume if you have a y signal of this time duration, let's assume I'm talking with you, so this may be like this. So this is time, so this is amplitude. If I plot the frequency spectra of this y, so it may be, I'm taking hypothetically this shape, so this may be the zero, this may be the voice, and then let's call this omega h, right? And this is your omega axis. So this is the frequency response of your y's. So let's assume this is your x of n and this is your xe to raise per j. So if we multiply it with complex exponential, and let me write it step number 2. This is your step number 1, step number 2. So if I write complex exponential e to raised power minus j omega naught n, and I take its Fourier transform, it will give me a pulse 0 at omega, only a single pulse at omega, right? So it's, you can see that its amplitude is 1, so its amplitude is 1. So if in third step, if sorry, this is step number 1, this is step number 2, let's make step number 3, and I mix the two signal. This is my y signal, and I multiply it with e to raise power j omega naught n. Sorry, this is plus not minus, right? E to raise power j omega naught n. If I mix or multiply my y signal x of n with e x x of n with e to raise power j omega naught n, then what will happen? So in frequency domain, my y signal get up from omega is equal to 0, and it will be shifted to omega naught. Entire signal will be shifted at omega naught, and this is x e to raise power j omega minus, right? So it will be shifted to omega naught, and my impulse will also be vanished, right? So this is the frequency shifting property or modulation property. Any confusion? So this
No,
is my
sir.
y
No,
signal.
sir.
It is around 0, but when we multiply it with high frequency, normally omega naught is greater than 0. Normally we can put omega naught is greater than 0. So normally in modulation, why we called it modulation? So let me write it here, modulation. So in modulation process, what you are doing, you are, let me draw the block diagram, and then in modulation, what you are doing, you are have m of t, and you are mixing it with AC cos of A cos of omega c t, right? So this is your modulation in time domain, a m of t cos of omega c t. So this, can anybody write this omega in terms of complex exponential? So you can take a common, and this would be e to raise power j omega ct plus divided by 2 plus e to raise power minus j omega ct divided by 2. You got the idea? So you
Yes,
have
sir.
two complex exponential rather than a single complex exponential. So here your omega naught is basically equal to omega c, and here your omega naught is basically minus omega c. So you just need to multiply. So that's why you are getting two peaks, one on the positive side, the other one on the negative side. So let me go to the next page and redraw it with respect to the cosine. So let me draw 3 steps again. So that's why it is called modulation property. Why it is called mixing property? Because you are mixing two signal. You are mixing m of t with complex exponential, or you are mixing with cosine. Why we are multiplying? In reality, we multiplying with cosine because complex exponential is complex, and cos is basically a real signal, right? So in reality, it is easier to handle real signal rather than the complex signal. So that's why we, in modulation, we are multiplying m of t with cosine. So let me do the same steps with cosine and multiply it, just to refresh your concept of modulation. I think you have done a lot in your uh, communication system course. So let me take a modulation. So let me take time and frequency different. This is time, this is frequency, right? So in, let's assume we have step number 1. We take the same x of n, This is your Y signal. This is N, so this is X of N. And its Fourier transform, we take the same Fourier transform. We take it on 0, so this is omega H. If we second step, we take complex exponential. Now we take a real signal, that is cosine. Let's take, this is cosine of omega ct and a cos of omega c. So if you take the Fourier transform of a cosine, now you will get two peaks, but their amplitude is half. This is omega c. Take minus omega c. But keep in mind, e to raise per j theta plus e to raise per minus j theta divided by 2. So its amplitude is half. Its amplitude is half. Right? So when you multiply it in third step, what you are doing, you are mixing two signals. So this is your Y signal x of n, and you are multiplying it with high frequency cosine. So what you will get in frequency domain? You will get one response here, one response here. You got, I think you remember your communication system course in which you have
Yes,
done
sir.
this repeatedly. So that's the difference. So once you multiply it with complex exponential, you can get the idea that if you multiply it with cosine, you will get this. And on the receiver end, if you multiply it with twice 2ac cos of omega ct in coherent demodulation, you will get back the signal. So this is the modulation property, or frequency shifting property, or mixing property. I remember the last name, frequency translation. This is heterodyning plus it. This property also known as frequency translation, because we are translating frequency from low to high. Frequency translation. So same property but with different name. Heterodyning, right? So why it is called heterodyning
Yes, sir.
property? Because in heterodyning, we are bringing the signal from higher frequency to the lower frequency. That is quite similar. We are mixing it again with the cosine signal, and the second cosine signal has a low frequency. So cos of omega 1t plus cos of omega 2t. अब जब दो different cosine को mix up करते हैं, so you will get 2 cos of alpha plus beta and 2 cos of alpha minus beta, and you will take the lower term alpha minus beta. So you will shift to the lower frequency. So frequency translation and heterodyning. Heterodyning के अंदर, super heterodyning receiver के अंदर आपकी frequency translation की property use है. So hopefully you got the idea about this property, and this is the backbone of your communication system. Why we do modulation? Why modulation is necessary in wireless communication? Why modulation is necessary in
मैं सर
wireless?
थोड़ा ऊपर करेंगे वरना नोट कर रहे थे.
Okay, wait a minute, beta. Why modulation is necessary in wireless communication? ठीक है बेटा?
Yes sir, बस.
Okay, we can hold for 30 seconds for you. Can I move?
Sir 2 seconds.
Okay. Wait.
Okay sir, move.
Okay, thank you. So why would you need modulation? Because you know V is equal to F lambda. right? And from here we can say lambda is equal to V by F. So higher the frequency, lower the lambda. ठीक है, जितना हम frequency increase करेंगे, so if we are going on increasing F, so our lambda would be decreasing, and your antenna size is directly proportional to, so your antenna size is normally lambda by 2. So if you have smaller the lambda, smaller the antenna size. So let me write it. If you have smaller lambda, so your antenna size will also be lower. So that's the reason we want our antenna to be as small as possible, because we need it for the transmission. And if there is antenna size is large, it requires large power, and that is not desirable in communication. Because in being a communication engineer, your job is to reduce the power and increase the spectral efficiency. This is your prime job. If you are a designer of your transmitter and the receiver, so one quality expectation from you is that you are going to design some system that needs smaller power and it provides higher spectral efficiency. Spectral efficiency means bits per hertz per second. So that's why you are moving to the higher modulation index. I think you have studied ASK, PSK, FSK, 4FSK, 8FSK, 18 QAM, 64 QAM, or 16 QAM in your communication system codes. And that's the only reason to increase the spectral efficiency, bit per second per hertz, because higher the modulation index, higher the bits you can pack in a given symbol. Anyway, so this is your third property. Let's talk about the convolution property. And this property says that if you are x of n, let me copy paste it from Control C. So x of n x e to raise for j omega. Sorry, x of n convolution. If you are convolving, so what you do in convolution, you are performing. Let me take the full equation and then I write h of n minus k, and your summation is running from k goes from minus infinity to plus infinity. If you're performing convolution in time domain, it is equivalent that you are performing h e to raise for j omega cross, let me use symbol cross, x e to raise for j omega. Let me copy paste it again. If you are performing convolution in time domain, it's equivalent that you are multiplying them in frequency domain. And it is again opposite. If you are multiplying x of n and y of n in time domain, better to use x1, okay, x of n, then you need to perform convolution here, right? So you need to perform convolution. Here convolution is different. Here you have x h e to raise for j omega. And your x e to raise for j omega minus. Right. X omega minus k. Right?
Yes,
So
sir.
this is convolution in frequency domain, or you can write this in short form if you want this in little bit short form. So you can say that if you are h of n equal to, and you can use this multiplier sign as a convolution x of n. This is equivalent. This is equivalent to this one, and if you are using this one, जिस तरह भी आपको अंडरस्टैंडिंग होती है, h e to raise पर j omega convolution h e. Change these symbols, that's this one. So this is simple multiplier is multiplier, and this is a convolution sign. So this is your convolution property, right? So if you have two signal in time domain and they are in series, you know that system in series. Let me explain it further with LTI system. LTI system. We know for LTI system, if there is an LTI system, this is h of n, this is x of n. So this is y. So your y of n is basically convolution of x of n and h of n. So if you are taking the Fourier transform of both, so if this is x e to raise per j omega in frequency domain, and this is h e to raise per j omega, then in frequency domain you can directly multiply y e to raise per j omega is equal to x e to raise per j omega into h e to raise per j. ठीक है बेटा?
Yes, sir.
Yes,
So
sir.
this property will simplify your problem. I'll solve one example after completing this property. So fifth property says that time reversal property. Control C. Property is the time reversal property. As in time reversal. Time reversal property is saying that if you have signal x of n and you know its Fourier transform x e to raise per j omega, if you reverse it in time, reverse in time mean that you are changing x of n to x of minus n, and its Fourier transform would be here, and just negative sign here. So this is the time reversal property. So let's take an example to understand this. We know that 0.5 to raise per n u of n. We have this example here. Large. Okay, let me copy it. Here. We know that x of n is 0.5 to raise per n u of n. Let me, okay, and let me remove all this. So this is x e to raise per j omega. So what will happen if we reverse in time domain? So if we reverse x1 of minus n, this would become 0.5 to raise per minus n u of minus n. And now its Fourier transform would be plus c to raise per j omega, because minus minus would be minus and minus again. Minus minus, let me do two steps for your clarity. So this would be minus. Let me add one more line here. This would be minus minus is equal to plus, so we can remove two signs. So this is the Fourier transform after time reversal property. Hope you got the idea that how this property would help to simplify the problem. ठीक है बेटा?
Yes, sir.
Okay, last property is the symmetric property. Symmetric proper. This property is saying that if you have x of n, if you have x of n is equal to this one, and if you take the conjugate of x of n, let me put conjugate sign here. If you take the conjugate of this one, so its Fourier transform will be the conjugate and the negative sign as well, right? So it's equivalent to the conjugate e to raise from minus j omega, right? For the real signal, it would be the same. For the complex signal, it will be the negative sign. So that's the difference between. So if you want to take the example, in our case, because this is a real signal, so you will get back the same signal. Let me solve the same example. If you apply this property to this x of n, what will happen? Let me take the conjugate of this one. So real conjugate is the same one. So there is no, this is a real signal. Conjugate of a real signal is same. I think you are familiar with this property from your complex course, complex system course, right? So here what you are getting, you are taking the conjugate and negative. Once you take the conjugate and negative, it would be the same one, minus j omega, right? So it is equal to the same signal, because for a real signal its value is same, because 0.5 to raise power n u of n is real signal. ठीक है बेटा?
Yes, sir.
So this is the last property of your chapter number 2. So with this property, I conclude chapter number 2, and tomorrow we'll start chapter number 3. We already started chapter number 3 for section C, and we cover left-hand sequence and right-hand sequences in the last lecture. Since we take one extra makeup class for C, but hopefully this Friday will be on same page. Any question from your side? If you pay little attention,
No,
that's
sir.
all. Do your assignments by yourself. I think you will get full marks in your midterm exam. I think there is no harm. Just you need to pay little more attention on this topic.
Inshallah, sir.
Inshallah, sir.
Let me take the attendance. You have no question?
No, sir.
Okay, let me stop the recording. Let me